Okay, so welcome back, everybody. We ended yesterday's lecture with this setup, so we wanted to consider, instead of infinite string, right, some kind of ideal string, this infinite string that came to us because our original consideration of this type of problem involved seeking a solution where x was just a real number, so from minus infinity to infinity, and t is greater than 0. So this setup here has us instead assuming that there's one fixed end, so that shows up as this boundary condition here, right? The reason I'm using v here is because in the analysis of what we're about to do, you'll see why I'm using v here, because I want to use u for something else. But I'm seeking a solution to this 1D wave equation. So as usual, I have my initial displacement, my initial velocity, but then this here, right, is a boundary condition now, which is something I didn't have before, because now I have a boundary. Before I was on the whole real line, so no boundary to speak of. Here, there's an end. Okay, there's an end here at x equals 0, and so at this end I'm saying that my displacement is 0, so it's a fixed end. Okay, and I wanted to consider how this boundary condition, how this changed problem affects the solution that I'm seeking. So the question is, can I just apply? So I asked this question last lecture, and I already answered it, but now we're going to think about it a little bit more deeply. So can I just use D'Alembert's formula? Well, there's a couple of reasons why I can't. So the answer is no, not quite. Right? Why not? So there's two things to think of. One, there's this fact that now the region in question is not the entire real line, but it's only half of the real line, right? Why does that matter? Well, if I were to, say, pick point here, x, right, and consider, say, I didn't draw this quite right here. Let me, there we go. Ignore that point. So if I were to consider, say, for this chosen x that I've picked here, if I were to consider x plus ct and x minus ct, then for this point indicated, right, xt, the relevant points that affect the displacement at the point xt are in this shaded triangle, right? This is my usual picture. This is my usual domain of dependence for this problem. But you'll notice that even though x is greater than or equal to 0, it's possible that this, according to this domain of dependence, I would need values here, right? I need some values here to tell me what's going on here, but I don't have these values because I'm restricting myself to x greater than or equal to 0. So that's one thing, right? So basically, like, according even to like the analysis from D'Alembert's formula, like what I need is I would actually need some info from these points that are not included in this domain. So that's one issue. The other issue is, how do I make sense of this? How do I impose this boundary condition using D'Alembert's formula, right? So like, What do I do with this? Well, to see the idea here, so we can start by kind of coming up with a solution mathematically as to what we should do. And you can think to yourself why physically maybe your intuition should tell you that this is the correct thing to do, but that requires a little bit more physics knowledge to think that this is what you should do. But mathematically, we can see that this works actually pretty quickly. So what is the idea? Well, I need info about points here, and I don't have it, right? Info here on the x-axis, the t equals 0 axis, right, is given by the initial data, right? T equals 0 is this x-axis. So any info I need about points here comes from the t equals 0 values, the initial values. That's what I want, right? So this is the info that I seek. So then I want to extend both phi and c to, they're defined on x greater than or equal to 0, but I want to extend them to the left half over here, right? I want to extend them to the real line, okay, in this way. So what's the idea here? The idea is there's an extension I could do by basically doing what's called the odd reflection. So if I have some graph you can think of for phi or c here, what I do to extend it is I just symmetrically draw the graph in a way that forces the extension to be an odd function. Okay? Of course, you might say, well, why did you choose odd instead of even? We'll talk about that in a little bit. But of course, yes, I could have done the even extension all the same, but I'm going to do the odd extension here. Okay? So let's do that. So idea, define phi sub odd of x and c sub odd of x, the odd extensions or if you like odd reflections of phi and c to the whole real line. Okay. So how do we do this? So quick definition. The odd reflections. And of course, I'm applying this to initial data. You could do this for any functions defined on, for x greater than or equal to 0. The odd reflections of our initial data are defined as phi odd of x is, well, it agrees with phi, where phi is currently defined. And if I want this thing to be odd, then when x is less than 0, I want this thing to be minus phi of minus x. Right? Okay, that should do it. And similarly, c odd of x is just c, where c is defined. And it's minus c of minus x on the left half of the real line. Okay. So now, of course, phi odd and c odd, we should note, are defined on the entire real line, right? Which was the main purpose. And they also, of course, are odd functions. Okay. And so, how can I obtain a solution to my IVP BVP here? The purpose of doing this is to now apply D'Alembert's formula. So now, idea, apply D'Alembert's formula to the wave equation. Okay. Now we know what D'Alembert's formula is, so we don't have to rewrite that. So say that we've already done that. Now, restrict this solution to the smaller domain, right, x greater than or equal to 0. So the idea is apply D'Alembert's formula to the wave equation on all of R that has initial displacement and velocity, these odd extensions of this initial data that we defined, right? And so that gives me a solution. I'll call it U. Now, if I restrict this solution to x greater than or equal to 0, the hope is that I get a solution to this problem on this smaller, right, subdomain of the real line. Okay. So for IE, for x greater than or equal to 0, define v of xt to be u of xt. But u of xt we defined using D'Alembert's formula for initial data phi odd and c odd. So what is this u of xt? This is going to be, just by D'Alembert's formula, this is 1/2 times phi odd x plus ct plus phi odd x minus ct plus 1 over 2c times the integral of x minus ct to x plus ct of c odd s ds, right? There it is. So the question is, does this work, right? I guess I should ask the question, does this work, rather than shouting at you that whether or not it works. So does this work? You can check that it satisfies the PDE. This is just because D'Alembert's formula satisfies the PDE, but you can check that it satisfies this PDE on the domain required. It satisfies the initial conditions. The question is, what about this boundary condition? So it is fine for the PDE. It is fine for the initial conditions. So then the only question is the BC. Is it fine for the boundary condition? Well, let's plug in the boundary condition and see whether or not this is 0. So v of 0t. Let's go back to my formula here. Here's my formula for v. Here. Okay. There's my formula for v. Let's plug in 0 here. What do I get? This is u of 0t. And now this is 1/2 times phi of ct plus phi of minus ct plus 1 over 2c times the integral of minus ct to ct c odd. Sorry, these are, what am I doing here? These are phi odd and c odd. That's very important. Because guess what we've done here, right? This sum is a sum of phi odd ct and phi odd minus ct. What happens when you have an odd function? You take the sum of that function at one value and then that function at the negative of that value. They cancel, right? This is 0. Similarly, what happens when you integrate a function on an interval that is symmetric about 0? When you integrate an odd function about an interval that's symmetric about 0, you get 0. So the fact that these are odd cause these terms to go to 0 at 0. So in fact, yes, this is 0. It satisfies the boundary condition as well. And so we truly have found a solution to this IVP BVP. Now, there's a slight thing to consider here, which is, okay, we've done this extension, these odd extensions in this way, but what is it that's actually going on? What if I actually tried to write this out? Well, there's two cases to consider. So if we try to write out v of xt entirely in terms of original phi and c, there are two cases. To consider. So the first case, now let's go back here to my formula. Here's my formula for v. So then what are the cases to consider? Remember, in my original case, right, this was the concern, that I pick an x that is greater than or equal to 0, right, for some fixed point xt. Well, for some fixed point xt, right, and of course you can, you could increase t if you wanted to. Even if x is greater than or equal to 0, I could potentially need some points over here in this domain of dependence to tell me what's going on here, right? And I don't have them. So it's purely a question of whether x minus ct is, right, I want x minus ct to be greater than or equal to 0 to be in my old case, right? Or I want x to be greater than or equal to ct. And if that's not the case, right, so that's one case, and I end up with a situation like this. So if x is, if this is the case, if x is greater than or equal to ct, I end up with a situation where I don't have these, right? I end up in a situation where my domain of dependence maybe looks something like this, right? Right, for some x1, t1. Right, so maybe I don't need, at this point, I don't need any info about what occurs to the left of 0 here. But if x is less than ct, I do. So these are my natural two cases that arise here. Okay. And so, of course, you might kind of think about this in the following way, right? Let me bring back this picture. If I'm in this situation where my domain of dependence looks like this, right? Looks like it did before. What can I say here, right? Well, I can say that this situation is exactly like it was in the problem that didn't have a boundary condition and was on the whole real line. That is, it looks exactly like the original 1D wave equation I solved on the whole real line. Why do you think that is? Physically, if we think about what's going on, I have string fixed at one end, right? And you can imagine string fixed at one end. The other end continues infinitely, or sorry, the other part of the string, right, it's going infinitely off towards positive infinity. So if I'm far enough away from this fixed end, then what is going on, I might reasonably expect to be similar to what's happening on the infinite string, right? If I'm far enough away from that fixed end, I might expect to not have to worry about the effect of this fixed end on the situation, right? So then the closer I am to this, maybe I do have to worry about what it is that's going on, right? But the further I am away, it actually starts to resemble more what I was doing before, right? You could think of yourself being like 10,000 miles away from this fixed end and question whether or not you could detect that there's a fixed end or not. Okay, and so anyway, I have two cases, right? So if x is greater than or equal to ct, that's one case, right? So then all relevant positions, right? All relevant positions s in this interval x minus ct to x plus ct, all of those are positive. So phi odd is just phi, and c odd is just c. And so what I get is exactly D'Alembert's formula. Okay, so this is 1/2 phi of x plus ct plus phi x minus ct plus 1 over 2c. And the integral from x minus ct to x plus ct of c of s ds, right? So I get something that agrees with D'Alembert's formula entirely. Okay. So when we're away from that fixed end, we actually that boundary condition has no effect on what's going on. So if we think about that hard enough, we should, think that's reasonable, right? That we shouldn't expect, being far enough away, we shouldn't expect that fixed end to have much of an effect, if any. And so the other case is if x is less than ct, how this works. Now, the relevant positions, or at least some of them, right, will be negative. And I mean, we know exactly where they'll be negative, right, in the interval when s belongs to x minus ct to 0, right? So exactly half of them will be negative. Okay. So then using the definition of the odd extensions of these things, what do I get? So v of xt is 1/2 phi of x plus ct. That's fine. That's at the end that's still positive, right? But now if I have, again, let's go back to what our v is, right? Here's v. So phi odd of x plus ct in this case, that actually still agrees with phi at that end because that's positive. But now at this end it's negative, so x minus ct is negative, so this should be minus phi of minus x minus ct, so ct minus x, right? So this is minus phi of ct minus x. Okay, plus 1 over 2c times, I need to split up the integral now, right? I have the right half of the integral, it stays the same. So this is the integral from 0 to x plus ct. I don't know why I'm pointing at this. Really, what I mean to be pointing at is something off screen, which is this thing that actually has the odd extensions here written in. All right, so here on the right half of this integral, my c odd matches c, so this is just cs ds. But on the left half, from x minus ct to 0, it's negative, so I have to use the odd extension. So this is plus the integral from x minus ct to 0 of minus c minus s ds. So let's be careful here. In this second integral, we can make a change of variable s to minus s. If we do that, the resulting integral is minus the integral from 0 to ct minus x. We can change that order of integration by incorporating the minus sign that we get out of that. And so what we get is, now we can combine these integrals together in the following way. So this is 1/2 phi of x plus ct minus phi of ct minus x plus 1 over 2c times the integral from ct minus x to x plus ct of c of s ds. And so we have actually found a formula to this original IVP BVP. It satisfies the PDE, the initial conditions, the boundary condition. The only difference, right, as to what's going on here is that I have cases now. If x is greater than or equal to ct, this is the formula it takes. If x is less than ct, this is the form it takes. Okay. Now, that might seem a little strange compared to the previous case, but it actually gets more complicated than this if we introduce another fixed in. If we have two fixed ins, you'll see that it gets substantially more complicated. So let's use these two formulas and this reasoning that we've done to think about causality with respect to the fixed end. Right? So causality for one fixed end. So what do I have to think of? Right? So one, if x is greater than or equal to ct, then this is just D'Alembert's formula, right? And our domain of dependence is exactly the same as before. So it's that shaded triangle like it always was. That's, again, we can think about that as if we're far enough away from the fixed end, then we don't expect to feel its effects in the same way, right? So then the question is, what happens if x is less than ct? Well, let's just look at our formula here. Now, what is going on here? Right? If x is less than ct, then the solution, which is, remember, this is telling me displacement, right? So then the displacement v of xt depends on, so this depends on initial displacement, which is phi, and initial velocity for which points? For string positions in the interval ct minus x to x plus ct. Let's see what happens here when I actually look at a picture. So rather than me spend the time drawing a picture, I'm going to show you a very nice picture in the textbook. There we go. Okay. So what is it that's going on here? Notice what would be the usual domain of dependence. You can view that as this outer triangle here, because if this is the point xt, then here's x minus ct, here's x plus ct, right? Okay, but of course I have mirrored, right, or reflected what's going on here in this way that what I actually need now are not, I don't need values here, and if you'll notice, I don't need values here either. From 0 to ct minus x, I don't need. They're irrelevant. All I need are values between ct minus x and x plus ct in this weird shape. Okay? So my domain of dependence is this thing, this region. Right? This little lower triangle here has been entirely snipped out. I don't need those points. Those are actually irrelevant. Because again, I only need the points ct minus x to x plus ct. Okay? And if I have those points, I am told everything, right? So initially, right, if I have those points initially, then my domain of dependence for a point here is everything in this region I'm indicating here. There's a better picture on the next page. So let me show you what happens in this case. So you'll notice that I have, let me get a little, there we go. So you'll notice that my domain of dependence is this figure on the left. Initially, I only need points between ct minus x and x plus ct. The region in question is this one, right? So at this point xt, what points do I need, right, in order to, or what points before, right, from my past dictate the displacement at this point? Well, all of these points indicated here in this picture. What's going on here is called a shadowing effect, where now these points have been rendered useless. I don't need them. Think about why that is and how this happens as a result of this reflection that we've defined. The other question, right, kind of the converse question, which is if I have an initial point here, what's the domain of influence, right, kind of emanating from that point? It looks like this, where this is not really cut off. It's only cut off because I have finite pages here, so this extends indefinitely. But it is this region. So here's the domain of influence for an initial point, right, on the x-axis in the xt plane. Again, all directly from these formulas, just like we got the previous ones directly from D'Alembert's formula for our original 1D wave equation. Okay, so let us see some examples here of this applied to plucked string and hammer blow examples. With one fixed end. Okay, so we have semi-infinite string here I'll give you an example of a particular choice of plucking here, right? So we have zeroed out the velocity, right? So c is identically equal to 0. And our initial displacement is given by this function, right? So don't pay too much attention to that. If we use the odd reflection for this thing to generate our formula in the same way that we've done before, the resulting picture looks like this. Here is my initial plucking, and you'll notice that this splits into two waves, one traveling to the left and one traveling to the right. But what happens when the wave traveling to the left gets to the fixed end, right? What happens? It is reflected, right, in this fashion and starts moving to the right. Oh, you didn't see the last one. There we go. So have a look at that image. Just see what it is that's going on and what the effect of this happens. So this wave traveling to the left gets absorbed, right, by the boundary, by this fixed boundary, and then its odd reflection gets ejected back and moves to the right. Okay. All right. What about the hammer blow? All right. What about the hammer blow? So for the hammer blow, we need to use even reflections, right? So fixing the left end results in an even reflection. So the even reflection can be carried out exactly like the odd reflection, and I'll mention that a little bit going forward, but this is the main point. Here, what does the hammer blow look like in this situation? So my left end is fixed again. Okay. Here's hammer blow. You can see how displacement is affected. Okay. Here I have movement toward the left. When it reaches the left here, actually what happens is now it moves back toward the right, and it's larger, right? It's moving back toward the right in this fashion. And that's because this fixed boundary has this even reflection property for this incoming wave. Okay, so the support of the wave doesn't grow. It just, once it gets to this size, it just stays fixed, right? So that's not what happened for the infinite string, right? And this is because of our restricted domain of influence that this happens. Okay, so now we have introduced the notion of boundary conditions, and they have already made things more complicated, but they can make things way more complicated than that. This is an example of what's called a Dirichlet boundary condition. So there are different types of boundary conditions that can be specified. So there is the Dirichlet boundary condition. So types of boundary conditions. Okay. There is the Dirichlet boundary condition, which is one like we had, right? So say u of 0t is equal to 0. Okay, this is a Dirichlet boundary condition. Just a condition on the displacement itself at the boundary point. Okay. There's what's called a Neumann boundary condition. So this is a condition on the x derivative at the boundary, right? So what is the idea here? If this is just telling me directly a condition on the displacement, so this is telling me that I have a fixed end. What is something like this telling me? So this is telling me that I don't have a fixed end. I have an end that's like attached to a ring on a frictionless bar. That's usually how it's discussed. And then the attached end can itself move freely up and down, but it can't exert vertical force on the string to the right. Okay. So at the end point, there's no vertical component of the tension force, and that's enforcing this. Okay. So I'll show pictures here in a second. Right. The associated, right, if I had a Neumann BC for a second, the associated IVP BVP would look like this. Right. This would be u sub tt equals c squared u sub xx when, so this is for x greater than or equals 0, t greater than or equals 0. And we have u, let's say x0 is phi as usual. U sub t of x0 is c on the same region. And then we have this Neumann condition. Right. Turns out that this can be solved analogously to our previous IVP BVP here. It can be solved in the same way here by considering even extensions. So this can be solved analogously to our previous case, Dirichlet case, via even extensions of the data. Okay. So there's another type of boundary condition called Robin boundary condition, which can also be thought of as like a mixed boundary condition, basically, where you have a condition simultaneously, right, on like a combination of the x partial here and the displacement, where a is some positive constant. This is kind of a more complicated thing. It's you have the end of a string is attached to a ring on a frictionless bar, but the end is also attached to the top of like a coiled vertical spring. The spring itself is like it exerts a restoring force, trying to basically pull the ring back to its equilibrium position. So you have a spring with spring constant, which is related to this A here, which is at equilibrium when its top is at the height, right? Exactly when the string is in equilibrium at our zero displacement point. Okay, but the left end is free to move. So the picture, if I can just bring this up real quick. Here are two pictures illustrating Neumann boundary condition and the Robin boundary condition here. Now, of course, you know, if you're just interested, like mathematically, in solving these things, then you don't have to worry too much about this. But this is nice to keep in mind as to where these things, what these things are referring to, or where these things arose in the first place. Okay. All right. Now, what else? So, Next, what about when both ends are fixed? What about when both ends are fixed? So, what does that look like? So, this would be a finite string boundary value problem. Now, this may be the case you're the most interested in, right? Because this is the case that more closely mimics what you're going to come across, right? If you're thinking of, for instance, like plucking a guitar string or something like that, right? I don't know how many infinite or semi-infinite strings you've seen, but you've seen plenty of finite ones. So it's natural that this would be a case you'd be interested in. But of course, this has some complications. Now, you could say, well, we're still in the case that this is occurring, right? And this is a 1D thing that we're doing, and we'll talk a little bit, especially later when we also consider the second and third 2D and 3D wave equations and how there are some differences, okay? And there are some fundamental differences in kind of the implications of solutions to those. And we'll talk about that when we get there. But for now, let's just consider the following. So our usual 1D wave equation, there it is. Except now this is for x on some finite interval, 0 to L. So I think of my string now having fixed ends at 0 and at L. And I consider the same equation. Well, as usual, I have initial displacement and initial velocity. So my initial displacement is phi. My initial velocity is c. Okay. For x living in the same world. Now I have, we'll say, fixed ends here. So displacement at the left end is 0. The displacement at the right end is 0. These are Dirichlet boundary conditions here. Okay. And so the question is, kind of the first question you're going to ask is, can we do a D'Alembert type thing? That is, can we use the kind of the same methods we've been doing this whole time to write down a formula for this, for a solution function that gives us the displacement here in this situation? The answer is kinda yes, but also no. Okay, so we can kind of sort of do it, but it's not really the way that you think, and it's not necessarily so nice. So what is the yes? Why do I say yes here? Because for fixed xt, we can, in fact, trace back all the reflections. So here, what's the main difficulty? As we're going to see very quickly, what is going to happen here is because we now have two ends. Remember what happened in the plucked string? Right? Remember what happened in the plucked string? We got this we got this reflected wave that got sent back, right? It got absorbed by this fixed end and sent back. Well, what's going to happen when I have two fixed ends rather than one? Right? I'm going to get multiple reflections here back and forth. Flipped and sent back in both directions, back and forth. That's basically what's going to happen here. And so in order to actually write down a D'Alembert type formula, for a fixed xt, I would actually have to trace how many reflections have occurred prior to this point. You'll see how one could go about doing this if you really wanted to. Okay, so for a fixed xt, we can trace back all the reflections to the initial data. And write out the formula. The D'Alembert-like formula for the displacement. For the displacement u of xt entirely in terms of phi and c. So yes, on one hand, you give me a fixed xt and I can do this. Okay. The problem with this is the following. So why did I say no? Because there's no one formula that works for all xt. Okay. So the problem is that if I give you any x here, like fixed between 0 and L, right? I give you any x here, then as t increases, the number of reflections increases. And so the amount of tracing back I'm going to have to do is different, right, for various t. So there's no single formula I can write down that works for all these things. Now, maybe you expected this already, right? Because technically our answer to this was actually already the same in the event of a single fixed end, right? Because in a single fixed end, we had two cases. So technically, we did not have a single formula that did it. But because there was only two of these, we tended to view them, we're kind of viewing them together, and let's say, oh, that's not so bad. The problem is that this case-by-case situation we did here, you would have to do this for several cases, right? 10, 20, 50 cases in the both fixed end situation. So that's what it is that happens. So there's not one single D'Alembert formula that works for any xt, but given a single xt, you can actually write out a formula for the displacement entirely in terms of the initial data. So the answer is kind of yes, but also no, right? And mostly no, I would say, because if you're hoping to write out one single formula that does it all, you're just not going to be able to. Okay, so now what I'm going to do is look at how this works in terms of the domain of influence. Right? So what about the domain of influence for this problem? What is it that's going to happen here? Right? So let's draw the picture first of all. Okay, so here's my x-axis, here's my t-axis. Right, here is when x is equal to 0, and we'll say L is like here. Here's L. Okay. If I have an initial point here, okay, what is the domain of points that this influences, right? So basically, I would have to consider characteristics, right, emanating from x naught, if you like, in both directions, and every time they hit these lines, you can think of these lines as like mirrors, basically. They reflect. And so what I get is something like this. Where the domain of influence is going to be something that looks like this, and it's only going to get more complicated as t increases, but it's going to be something that kind of looks like this. So I have an initial disturbance, right, with initial displacement and velocity here at this x naught. And the question is, what is it that's going on? Well, then both of the characteristics here that I think of, remember my wave equation, me factoring my wave equation, and thinking about this as two transport equations, the corresponding characteristics, right, x plus ct, x minus ct, what does that look like here, right? Well, I have lines that look like this that get reflected off of these boundaries, right? So one at 0, one at L. And the region in question, the points that are influenced by initial data here, provided here at x naught, are all these shaded points that I have listed. There's a really good picture in the textbook. Oh, why is it it's very bright. What's going on? There we go. Okay. So, here's what the domain of influence looks like. Okay, on the right, I'm dividing up our space-time here in a way that allows me to do what? So this I have labeled in each region here the number of reflections needed to connect back to the initial data. So in this region, notice I don't need any reflections to connect back to the initial data because the initial data is provided right here, so I don't need to worry about reflections. But in these two regions, I have one reflection each to get me back to the initial data. In this region, I have 2, 3 here, 4 here, and you can count on and on in this way. These are how many steps you would need to trace back to the initial data if you wanted to write out this D'Alembert-like formula. But you could do it. You could do it. If you were willing to trace through these things, you could actually write out your D'Alembert-like formula in this way. Okay, you could work backwards in time, trace back these reflections back to the initial data, and write out everything in terms of some D'Alembert-like formula. Okay, now, question, surely there's a better way of doing this, right? How are we going to go about solving this? How are we typically, maybe, going to solve such a problem? Okay. The answer is there's a method. Separation of variables. That provides solutions to such problems. And it's by seeking solutions in a very special form. Okay, so this turns out, once we've seen how this works, this turns out to be much simpler than doing it in this way, writing this D'Alembert-like formula. This is going to turn out to be much simpler than a D'Alembert approach. But the techniques that go into this can kind of be developed all at once for all of the big three equations. And so we're not going to do it yet. We're going to have a look at the other two big three equations first, We're going to have a look at the heat equation and Laplace's equation, and then we're going to worry about the specific methods for separation of variables. Okay. All right, and so in fact, if I were to just give you, right, like where did I write my finite? Yeah, there we go. In fact, if I call this star, right, I can show you a solution to star right now that is not in some hideous form. Okay, it's actually in a really, really nice form. So if here, I had plenty of room here. I don't need that. So in fact, if we'll say phi of x is equal to sine of, we'll say 27 pi x over L, and c of x is identically equal to 0, then the unique solution to star, which is this finite string boundary value problem. So if phi is sine of 27 pi x over L, and c is 0, and we have these 0 boundary conditions, unique solution to this is given by the following. And the unique solution to star is u of xt, which is sine of 27 pi x over L times cosine of 27 c pi t over L. So you can check for yourself that this actually works. In fact, I encourage you to do it just to verify I'm not lying to you. This solves the boundary conditions. So to see that it solves the boundary conditions is pretty easy. Plug in 0, I have sine 0. Okay. Plug in L for x, I have 27 pi. Sine of 27 pi is also 0. Yep. So it definitely satisfies the boundary conditions. It definitely satisfies the initial conditions, right? At t equals 0, so at t equals 0, this is cosine 0 times sine of 27 pi x over L, which is exactly phi. Taking the t derivative here and evaluating this at t equals 0, I will get 0 in this case, right? Because this will turn into a sine, right? And then sine 0 is 0. So it satisfies all those conditions. So then you can quickly check for yourself that it also satisfies the wave equation. And that's it. We're good to go from that point. Okay, now, how did we arrive at this? Well, separation of variables, as I said, which we'll do later. What's the thing that should kind of clue you in on this being very special? Well, the variables are separated, right? What has happened here is I've sought a function where I can separate x and t in the solution as a product of a function of x and a function of t, right? And in particular, for a fixed time t, this solution is just some constant, right? Some cosine of blah, right? For a fixed time t, this is a constant. So it's some constant times my initial displacement. Okay. So we'll talk a little bit more about that when we kind of return to this later. In fact, we'll do this specific example to show that indeed this is this is the unique solution that we seek. This will be the first wave equation example we do when we talk about separation of variables. Okay. And so that is mostly all I wanted to mention from Chapter 3 stuff. I'll say that some final remarks on Chapter 3. So some final remarks on the 1D wave equation. The reason why we spent so much time on the 1D wave equation versus some of the other things we're going to do is because it is basically the easiest to understand what is going on everywhere. That's one reason. The other reason is the same reason that we are going to, it's the same reason we're going to talk about actually the 2D and 3D wave equation next, is because the wave equation has something called, we'll call it like finite speed propagation, right? And the reason why this finite speed propagation is important to us is because it matches the most with first order equations. Okay, so everything we did with first order equations and the method of characteristics is kind of mirrored or closely matched by not entirely, it's not really mirrored, but it is more closely related to the methods that we did for first order PDEs than it will be for the other two remaining PDEs. So the other two remaining members of the big three second order PDEs, the heat equation and Laplace's equation, they act a little bit differently, and we'll talk about that when we get to them. But there's some characteristics they have that act slightly, and I don't mean, no pun intended. There are some properties, maybe I should say, instead of characteristics. There's some properties they have that are a little different and warrant us treating them later. So anyway, that's one reason. Another thing, why call it the wave equation? The wave equation. It's mostly historical reasons. As we've already seen, the Inviskid-Burgers equation, like this thing. This was an example of a wave equation because, in fact, what we used it to model was like a wave breaking on a beach, right? That was kind of our motivation for drawing pictures and looking at this thing, right? And this is a first order equation. So what's the deal here, right? Why call this why call this, why not call this the wave equation? It's purely a historical thing. Of course, what we call the wave equation does in fact model a lot about what we think of when we think of, like, for instance, propagation of sound waves in 3D. 3D wave equation is great for that, but it's by no means the only wave equation. There's plenty of, in the sense that it's not the only equation that models propagation of waves, clearly, because we had one in Burgers' equation. If you wanted to talk about, for instance, the Schrödinger equation, Klein-Gordon equation, telegraph equation, Korteweg-de Vries equation, those are all examples of other wave equations, right? So Schrödinger, Klein-Gordon, telegraph, KdV equations are all wave equations in the sense that they model propagation of waves of some type. And so this, you don't have to think that the wave equation is like the single equation that models propagations of waves. It's just what we call it. Okay, just like in the textbook, the author goes out of his way to almost always refer to the heat equation as the diffusion equation, which probably makes sense because if you call it the heat equation, maybe people tend to think that like heat, like heat flow is basically the only thing it models. Of course, it models really diffusion in general, and it can be like it's ridiculously prevalent in so many applications. I can't even list them all. But heat is easier to say than diffusion, so a lot of times I will just call it the heat equation. But understand that it's not, it's not just for that, right? Okay. So anyway, that's more or less all I wanted to say, apart from, like I said, note the wave equation satisfies, what should we call it? Fixed finite propagation speed. Okay, for say any disturbance, any signal. Okay. So the reason why it's interesting or it's notable to at least like extract out this property and put it under focus is that there's plenty of other of wave equations, as I've mentioned, that have this same property, this finite propagation speed. A lot of those equations are nonlinear. Okay, and anyway. The question is, what do I mean by fixed finite propagation speed? Like, what's the alternative, right? So the idea here is there's an initial disturbance. That disturbance, that signal, propagates at some fixed finite speed. Okay, so in the domain of interest, right, there's a fixed finite speed at which that signal propagates, and so that signal is not going to instantaneously reach, say, some given point, right? It needs time to propagate at the speed until it reaches the desired point in question, the point you're talking about. So what's the alternative to that? As we'll see, the heat equation, Laplace's equation, satisfies something, especially if we can talk about the heat equation, in a sense, satisfy like infinite propagation speed, which might cause you some distress at first. You say, well, infinite speed. That doesn't sound right. That sounds like that violates a few laws of physics I can think of. Right? Infinite propagation speed. What's meant by that? We'll see when we get there, right? So we will talk about this when we get there. It's actually an interesting discussion, but we'll talk about that when we talk about the heat equation. So anyway, this fixed finite propagation speed is something that we saw in the method of characteristics for our first order PDEs, and that's the reason why the wave equation comes first in our study of the big three. Okay, so now on to the 2D and 3D wave equations. Okay, and so on to chapter 4, which is 2D and 3D wave equations. So what are we doing here? We can just do these simultaneously at once. So the idea is wave equation in n dimensions right, Rn is what? This is a second order PDE. We are solving for displacement u of xt. This x is a vector in Rn, so x has components x1, x2 up to x sub n. Okay. T is some scalar real number, right? What is the wave equation in n-dimensional space? It is u sub tt is equal to c squared times the Laplacian of u, right? Where this is the Laplacian, as I've mentioned before. So what is the Laplacian operator? The Laplacian of u is defined to be the divergence of the gradient of u. So this is the sum of the pure second order partials. Right? So this is u sub x1 x1 plus u sub x2 x2 and so on. U sub xn xn. So of course in 3D, which is actually what we're going to start with, you might find that strange, but basically how we're going to address the 2D and 3D wave equations is, rather than, we're not going to talk about them in anything approaching the depth that we did the 1D wave equation. In fact, you're going to ask a question when I write it down. You're going to say, does it have a D'Alembert type formula? I'm going to say, yes, it does. It's called Kirchhoff's formula. And that formula is going to give us a description of displacement in terms of our initial data in some way. And then we're going to talk about what Kirchhoff's formula means, what it implies about causality and all that stuff. We're going to see how the 3D formula gives us a 2D formula. We're going to talk about the differences between those, and then we're going to move on. So we're not going to do the same sort of thing because it's a lot more involved. We'd have to spend a lot more time on it, and it makes more sense to return to this later when we have other tools in our toolbox. So how does this work? The 3D wave equation, what is this, right? This is, well, it's u sub tt is c squared Laplacian u, but the Laplacian of u here is c squared and is u sub xx plus u sub yy plus u sub zz. Okay. Of course, if you like to write it all on one side, you could do that as well. This is u sub tt minus c squared Laplacian u is equal to 0. You could also write it like that. That's fine. Okay. All right. I'm not going to derive this. If you want to see derivations of this, so derivations. What pages can you have a go at? You can derive it from Maxwell's equations. This is page 124, 125 in the textbook. This is Maxwell's equations. In fact, the homework, I have you kind of doing a backwards thing, showing that if you have two vector fields E and B satisfying Maxwell's equations of a particular form, then the functions that arise from those in terms of xt solve the 1D wave equation. It turns out actually that you can actually show that all the components of those things satisfy the 3D wave equation using this terminology. So if you want to see how that goes, you can have a look at page 124, 125. So in fact, one way of deriving these is from Maxwell's equations. There's another derivation that's done later, right after that. So this is the derivation immediately follows is page 125 to 127-ish. So 125 to 127 is a second derivation that does not use Maxwell's equations. So in the event that you feel like using Maxwell's equations is too much machinery or too high powered, you can have a look at another derivation if you like. Okay, the derivation, this derivation is from Maxwell's equation. The second derivation is from the Euler, considering acoustics and the Euler equation. Okay. And so, natural question, and then we'll stop for today. So, what is the IVP for the 3D wave equation? Oh, sorry. It looks like this. So u sub tt is c squared Laplacian u, where x is in R3, t greater than 0, and I have initial data just as before. It's phi of x, and I have initial displacement phi and initial velocity c, right, for x in R3. Where B and C are smooth. Okay. Here, of course, this vector x denotes vector with components. We'll say x, y, z. So we're in the 3D case. So natural question is, does there exist? Notice there's no boundary conditions here. These are just initial conditions. So does there exist a D'Alembert type formula for the solution u of xt for this IVP? I mean, you know, because it's the only thing you know for second orders, this is always going to be a question you keep asking, right, until you get an answer that kind of completely clashes with what you expect. So can you write out D'Alembert-like formula for the solution to this IVP, right? And the idea that it's D'Alembert-like means in terms of phi and c entirely, right? So just in terms of the initial data. And the answer is yes. And this is exactly what Kirchhoff's formula is. So what does Kirchhoff's formula say? Kirchhoff's formula says the solution to, we'll call this asterisk, the solution to asterisk is the following. U of xt is 1 over 4 pi c squared t squared times the integral over the surface, which is, this is actually a sphere, of the ball centered at x of radius ct. We'll talk about this next time. Of phi, I'm going to use a dummy variable here, phi of y, to indicate that I'm actually doing a surface integral over this surface here, plus the gradient of phi of y dotted with y minus x plus t times c of y ds sub y. That's just to say that I'm doing this as a surface integral, and the parameter I'm using here is y. We'll unpack what all of this means next time, okay? But the idea is you'll just have to believe me for now until next lecture that this actually works. You might immediately see, wait a minute, and t is equal to 0. Oh, I'm dividing by 0, right? I have 1 over 0 is times some stuff here at t equals 0. So it doesn't even appear like this satisfies the initial conditions, right? In fact, it's not even defined at the initial conditions, it looks like. So how could this possibly work? Well, we'll see next lecture, okay? So anyway, that's all for today. So, let me know, as always, if you have any questions about anything, and I will cover those things or talk to the tutor and have him cover those things. But anyway, just let me know. So I will see you all later.